Hey everyone, welcome to this video where I will explain the general concepts for the Calc 2 Exam 2 materials. This applies to both MA 162 and 166. Some minor differences here and there, but generally you learn about generally the same thing. So first, finish off with more physical applications of integrals. And this is like, so you probably did the first part for exam 1, and then this part is more integration, just more complex integration. And second, we have integration by parts, which is really important, and you might use it later on after Calc 2 in other science classes or engineering classes. Um, and then integrate using trig. So this is a little different than 4, which is trig sub, but trig generally just using trig identities and substitution, and 4 using trig sub, generally just draw a triangle and figure out the different what a different cosine or secant stands for which side and stuff like that. For the fifth concept would be partial fractions, another pretty important integration technique. And then finish off the integration part with improper integrals. And then finally heading on the intro to sequences and some series, I think. So starting off with more physical applications. So we have sort of this general concept of the work being done by a water pump that is pumping water out of a tank through the top, right? So um, let's say you have like a water pump right here, and it's like pumping the water out of this tank this way. So generally, like it's pumping like the top water out first, um, and like so it's doing less work. It's doing more work as it works the way down, right? Because the water is needs to go more distance up, um, and 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 that work will be differentiated based on the height of where that water is from, right? It doesn't matter if the water is like over this side or this side. If it's the same height, it should generally be the same work since um, uh, for physics, right, the work is you doing work against a force, right? This force you're doing work against is the gravitational force on the water. So you're working upwards against the gravitational force downwards. So therefore, your work would be differentiated by the up-down direction, which you, in this case, I have it as y, right? So I have here total height is h. I said h. Length will be L over here, and width will be W. Y will be the axis we were saying that the height is in, right? Rho is density, G is gravity, the gravitational constant rather, and Y is where um, I'm saying the height of a certain level is. Right? So from that, um, I will splice this into very thin layers. I'm gonna call the height of each layer dy. Right? It's really small. It's just like a paper thin layer. And for that, right, I'm going to calculate the force on that layer, right? For the gravitational force, right, it's calculated by mass times gravitational constant, right? And then mass, I can calculate mass using volume times density, right? Volume times density is mass, and then I can get volume by multiplying length, width, and height, right? That's since we have a rectangular um, sort of form. Uh, so that's gonna be my general concept, general approach to calculate the force, right? Once we have the force, then we can just times the distance, right? The distance away that it's doing. The force is gonna act on the object on. Then I can just integrate that, and I can get the work that's done on um, the whole water tank. So we have all these, right? The distance, right? The distance will be how far away it's from top. So I'm doing h, which is the whole thing, minus where it's at, which is y. So h minus y will be the distance for that singular layer. Um, and in that case, then I will write out all that over here. I'll put it in here, right? Work is the integral of 0, saying the bottom is 0 to h. The whole water tank has height of h, and then length times width times dy. That's the volume of one singular layer times the density. This part will be the mass of one layer, and then times the gravity will be the net gravitational force on that one layer, and then times the distance. Then that will be the work done to remove that layer of water from the water tank. And once you write this out, right, you can move dy outside, right? And then, you know, um, this is a constant, this is a constant, density a constant, gravitational constant is a constant, h is a constant, right? Only y is changing. So this is actually, once you plug every number in, it should just be a simple chain rule on this y, and then you can get that work. Just might seem a little bit complicated. You just draw the graph and understand. Sometimes it might be not be a rectangle. It might be like a pyramid. Pyramid where it would be um, maybe it might be triangular pyramid or like um, whatever. You just have to understand how to calculate a volume of a single layer, right? And then the rest should be the same. Moving on to hydrostatic pressure. So this is similar um, for it might be like in this case it would be calculating like the pressure of like a point, or how much total pressure are you applying on, let's say, the bottom of this water tank. It might be a trapezoidal shape, right? Uh, it can be any shape, but you just need to understand how to calculate for, like, let's say, a volume of like a single layer and how the depth is varied, right? Generally, the hydrostatic pressure is just rho gh, right? Density times gravity times the depth of that layer. Just gotta be careful. Depth is from top, right? It would be like this. So if the whole height of, let's say, this water tank is h, then this part is y. Let's say if you have 0 being right here as ground zero, then the depth would be h minus y. And then you can integrate like throughout the layers. Then you can get a total pressure. Same idea as the um, water pump. Just calculate a different thing and uh, a different direction, I think. So moving on to biparts. Oh, right, biparts is generally thought of as just product rule in reverse, right? Product rule of, like, let's say you're differentiating uv, then it equals to u dv u dv dx plus v du dx, right? So in that sense, it's in reverse as that u you have like a you're integrating like a u dv, um, then it's like this part. So if you can sort of imagine, for the product rule, if I multiply dx on both sides, right? Then it's something like u dv, and I can move the v du towards the other side, right? Minus v du on both sides, right? All the dx cancel out, and then I integrate all of this, right? I integrate each part, and then you have this integration and the differentiation cancels out. So you have uv minus vdu, integration of vdu equals to udv, right? Which is what biparts is. So, and it's pretty simple to memorize, right? The integration of udv equals to uv minus vdu. So it's the product of each minus, right? Minus pretty important here. Um, the integration, but in reverse, and it's udv, right? So the next important thing for biparts is how to choose which part of the equation you choose as v. U, sorry. U, uh, you choose a part of the equation as u. I'll go through an example later, but L'Atier is generally the rule, right? It's log inverse trig, algebraic, so it's like x to n, x to the second, x to the fourth, um, and then t for trig, cosine, sine, tangent, all those, and exponentials. So you go down the list. If you have, let's say, two parts of a integration that you have, one is log and one is trig, then you want to pick the log part as your u, and the trig part would then be the dv. So let's go through an example. In this part, we have a integration uh, of, that should be a multiply, not a minus, x times natural log of x, right? It's for biparts, usually there is like multiple parts that you can sort of see that's like different from each other. So in this part, in this we have natural log and a x, right? The x is algebraic, and then natural log is a log. So from the L'Atier, we choose natural log as our u, right here. Generally, drawing something like a 2x2 table here might be helpful, right? Write out u equal to natural log of x, right? That will be up here, and then for the across, and then you can write dv as x dvx, right? Whatever, these two boxes should be filled out first, right? Because that's the given part, the udv part. Um, I should draw these. But so right, fill out this first, this box first, this box second, and then you can do the other two wherever you like, right? Uh, Three, I choose to do the differentiation first, right? So du then would be 1 of x. For that's natural logs differentiation dx, and then integrate dv, right? This box, then you get 1/2 x squared, and then you can write um, like this differentiation then equal to u times v. So I have u, I have v, that it's ln x times, oh, it should be here, times 1/2 x squared, that's uv, minus differentiation of u is here, I mean v is there, 1/2 x squared times du, which is 1 over x dx. Alright, then here you can see that the 1 over x and the x squared cancels out once, and then you have a nice 1/2 x, which you can do just with chain rule, and then you don't have a sort of two-part integration you have to worry about. This nice thing about biparts, if you're able to do it, it will become very simple. Um, by the end of that, if you choose the wrong u, it might be a little more complicated, but you should still come up with the same answer. And practice makes perfect, right? If you practice a few questions, you'll be able to like find the feeling on like which one should be u, which one should be v, and then that will help you, you know, on the exam to do these questions quickly. And you know, this can be solved with for trig methods too, right? But sometimes there might be like infinite loops because you can take like a u, let's say like you have a u of like cosine x, and then you take the du, and it becomes like negative sine x, and you take that derivative again, right? You might have to do by parts twice. Then it becomes negative cosine x again, right? It's what I'm pointing out here. So for an equation like e to the x and cosine x, right? You might first have a cosine x as your u, right, from the uv multiplication, and then again, um, that du becomes another u, um, and then you have a sine, and then you do that again, the udv part, the vdu part, then again has a cosine in it, and you realize at that point that this is the infinite loop, right? You take more by parts this multiple times, it comes up just alternating between cosine x and sine x, cosine x, sine x. Then you can sort of just see that this part, right, e to the x cosine x is same as the original question. Then what you can do is you just move this. This is an equation, right? The left side equals the right side. So you can add this orange thing to both sides. Then you have two integral of e to the x cosine x dx equals to e to the x cosine x plus e to the x sine x, right? And then you divide 2 by both sides, and then you're done. This is your answer. That's quite genius, isn't it? Right? Sometimes you just gotta break the loop, and then uh, sometimes you might have some constants, right? If you have like a 4 here or something like that, then chain rule will have like random 4s somewhere. Maybe it's like you have a 4 in here, then you have like 16, and then like 64. But um, the general idea will still be the same, right? You will have like some random numbers. Let's just say 64, and then you add that 64 over. Then it will not be like nice with 2, but it will be like 65, something over 65, and then you're able to solve that question. Moving on to trig integrals. So first part is dealing with sines and cosines. Right, the central idea for this is that the identity, the trig identity of sine square x plus cosine square x equal to 1. Right, x can be any angle. This will hold true. Right, for example, if I have to integrate 1 over 1 minus sine x dx, what I can do is I can multiply top and bottom by 1 plus sine x. And what this does is that this completes this the square, the difference in squares, right? Top will be 1 plus sine squared. 1 plus sine x. And then bottom part would be 1 minus sine squared x. Right. If I have sine out here, a squared minus b squared, that's just a plus b times a minus b. Right, I have this part. I'm artificially adding this part to get a difference in squares. And if you rearrange this trig identity, right, if I minus sine squared x on both sides, then we get cosine squared x equal to 1 minus sine squared x, which is the bottom part, dx. So then we have 1 plus sine x, and then 1 minus sine squared x becomes cosine squared x dx. Right, and then I can split the top part into two fractions. So integral of sine squared x plus the integral of sine x cosine squared x dx. Right, this is secant squared x. And then this becomes tangent x, right? Gotta memorize the all the integrations for integrations and derivations of different um, trig trig identities. So you can see that these things are related from like integration to just differentiation. And then here, uh, this part should be u sub, right? We have u equal to cosine x, then du will equal to negative sine x dx, and you can see that sine x dx, right, is the top part. So you can use, it'll be like 1 over u squared, and then you should be able to solve it from there. The other part of sine and cosine is when you have sine and cosine, and then there's like higher powers of it. So like in this case, we have sine x to the m power and cosine x to the n power. One is m and n, right? And then so we have two cases. One, m or n is odd, right? There have to be integer and positive. That has to be. But if one of them is odd, you can split sort of one of the power off from the odd. And I'll show you. You can choose if both of them are, you can kind of choose which one. But in this case, I have sine x to the third and cosine x squared, right? So in this case, sine is the one with odd power. I can split one off. I have sine squared times sine x times sine squared x times cosine squared x, right? And then for this sine squared x, I'm going to use the central idea again, the trig identity. I'm going to convert that into 1 minus cosine squared x. Right, well, keeping all the other things the same. I'm actually going to move the sine x in the back. So I'm going to break this into two integrations. Right, 1 times cosine x squared times sine x, which is be cosine x squared sine x dx minus cosine to the fourth And this is a simpler version of the trigs to solve, since you can do u sub. You can u sub a cosine, then du will be negative sine x dx. Same situation as the other one, right? This will be replaced with du of sort, right? Same with this part, and then you just have a u squared and then use the fourth to deal with. And then you can solve the integral, which is much simpler than the other case is when you have both of them, both n and m are even, right? Then you need to use identities. Let's see. Um, so we have cosine squared equals to 1 plus cosine 2x over 2 sine squared x go to 1 minus, sorry, goes to 2. Um, these two are like from the double angle formula. It's from cosine 2x equal to um, uh, 1 minus 2 cosine x. I think that is it. I'll have a separate video going through all the trig identities that's relevant to this exam, because there's a few of them, and I will derive each of them so you can know where it comes from, and hopefully that will help you remember some of these, because these are really important, and like the negative sign here and the positive sign here, sometimes you can get that mixed up, and then you not have uh, a fun time. So go through example. Let's say we have sine square x, cosine square x. Right, both the powers are even. So what we can do is we can replace the sine square x with 1 minus cosine 2x over 2 times 1 minus 1 plus cosine 2x over 2. Alright, since you can see that this is like sort of downgrading the power of those trig functions, right? From a square, now it's a now it's just in the first power, and this is much easier, way easier to deal with, right? In total, right, this is another sort of completing the difference in square. You get 1 minus cosine squared over 4. Oh, right. And then, or you can split the fourth off, and then this into two fractions, and then that. Actually, you can just use the trig identity again. Have this, right, and then you can use the double angle identity, the one, this one again, since you have sine squared x, sine squared 2x, and this will be, let's just take the fourth out, 1 minus cosine 2 times 2x over 2, right? Now you have just a cosine of of first power, then that would just go into like a negative sign of sort, and then you can solve that.
uh, Tangent and secant related trig integrals. So the central idea is still the same. It's the sine squared plus cosine squared at an angle is equal to 1. But in this case, we will divide both sides by cosine squared. So the sine squared divided by cosine squared would just be tangent squared, since sine x, sine of any angle divided by the cosine of any angle equal to the tangent of the angle. And the square would just make that squared. Cosine squared cancels out, and then 1 divided by cosine squared is just secant squared. So we arrive at tangent squared plus 1 equal to secant squared. So this is another trig identity that I urge you to know. You don't have to remember this. You just have to remember where it comes from. Right? It comes from the original trig identity, and that divides by cosine squared. If you forgot, you can always make this, right? You just got to remember tangent is sine divided by cosine. And the other two identity that you should probably know is the derivative of tangent and secant, right? These should be from calc 1, I think. And right, the derivative of tangent x is secant square x, and the derivative of secant x is tangent x secant x. And that will come in handy as you do integrals. You go the other way where you u sub later on with trig sub or anything like that. That would be still coming pretty handy too. So for example, same idea with sine and cosine, right? If I have a, like let's say like odd power, I can make the I can make a secant squared minus 1 using like a tangent squared, right? So I can first separate this third power into a tangent x and a tangent square x. And then tangent square x is, if you move the 1 to the other side, is secant squared minus 1. And then you distribute this out into two different integrals. You have tangent x, secant square x, right? And then in that case, we can u sub for tangent x, right? Then dx will equal to du will equal to secant square x dx, and then that is a pretty simple integral. You plug the u back in, and that should be pretty easy. And the other one will just be tangent x, right? And then tangent x, what you do is you make it sine squared over cosine squared, and then you can make u sub of u equal to I'll just write it down. U equal to cosine x, which is the bottom part, right? It's sine over cosine. So then du will equal to negative sine dx, and then that's the top part. So it'll be like 1 over u, which would be like ln cosine x, or rather negative of that, plus c. And then that's the way to solve it. It's generally the same with how the sine and cosine part of this trig integral works, right? It's when there's even powers, right, you can just like kind of distribute those and then figure out what your du is going to be. And so you have like in this case where du will be like secant square x or like a cosine x, or like sine x in this case, and that you convert everything else into back to what u needs to be. Like for this case, u is tangent x, or if you have like a tangent to the fifth power, and then you have like a secant to the fourth power, right? You convert like a tangent square into a secant square. You could do like a tangent square, and then you have u equal to tangent x, and then go from there. Right, and then that's kind of what I talked about. So for similar to sine and cosine, right? And then And then the other part is if it's you have like an odd power, then you can consider using secant x as a u, because you can have secant x tangent x as a du. Then you can write that aside, and then you should have like even if you take out like one of the secant square or tangents, secant x or tangent x, then you will have an even power, and then you can convert that all to tangent or secant, and then use up from there. And the other tip I'll give is that try to be flexible. And I get that this comes from more practice and recognizing when you can convert, like let's say 1 over cosine x to secant x, right? 1 over sine x or cosecant. And the other one is obviously pretty important too. The um, sine over cosine is tangent. And I would say if like you would get stuck on something, maybe try converting like this, and then see if you can see something that can help you. So then we move on to trig sub. So trig sub is generally for questions that have like a square root in the bottom. Sometimes it doesn't. Sometimes you can make that square root by like square root and then squaring. So you're canceling out, but you're just use something, and that also takes practice and recognition. But this is when other methods don't work, right? Trig sub is pretty cumbersome, I would say. But when byparts doesn't work, when u sub doesn't work, when there's no trig involved that you can see, that's when maybe you can consider trig sub. So the central idea is actually just a triangle, right? Or a right triangle rather. It's the idea that c equal to the square root of a squared plus b squared for a right triangle, with c being the hypotenuse, and we have a arbitrary theta here, in which the sine theta is the b over c, right? Opposite over a hypotenuse, and the cosine theta would be a over c, and that is generally what you can trig sub, right? These two connects what you have, which would be in the ABCs, to the angle that you're subbing, which will be the trig part. And in this case, let's go into like an example. So we have this integral of 1 over square root of 1 minus x squared. Right? This cannot be u sub, because if you sub 1 over x squared, you need like an x on top of the fraction. But you don't have that. So in this case, we can actually draw a triangle, and in this case, if we say the hypotenuse is 1, and the opposite of the theta angle is x squared, or rather x, so then the adjacent side of this theta would just be square root of 1 squared, which is 1, minus x squared. And you see that this part really comes out for this bottom part, the square root of 1 minus x squared. It's a cool, clever way of getting at this. So here we can connect theta with x by using theta. Sine theta is x over 1, right? It's the opposite over hypotenuse. And then connect it with dx, right? Take the derivative of both sides. We have cosine of cosine theta, d theta is dx. And the other connection we have is the using the adjacent side would be cosine theta, right? And then we can plug that in. We can plug cosine theta in for the square root part, and then we can plug the dx for the d theta. So right, we have this dx part that goes here, and then this that goes here. So we will result in, now when we sub it in, we have 1 over cosine theta d theta. Right. Always remember to sub in the d theta. You should always have just one variable that you are integrating over in calc 2. So right here, cosine theta is cancel out. We just have integral of 1 d theta, which should be just theta plus c. That should be a c. Right, and then you can plug this back in. Right, we have sine theta equal to x. So I can take the sine -1 of this. So then theta will equal to sine -1 of x. That should be x. Right, and then the plus c will remain. So that's case 1, right? Case 1 will have, in the square root, we have 1 minus, or a perfect square minus another perfect square. 1 is a perfect square, and x squared is a perfect square. In that other case, we have a perfect square plus a perfect square in the square root. So in this case, instead of using the hypotenuse and the opposite of a angle theta, we can use the adjacent and the opposite of this this angle theta with 1 and x. Then the hypotenuse will just become the square root of the sum of their squares. All right, that's just Pythagorean theorem, and then you can get the nice plus sign in there instead of the minus in the hypotenuse minus the opposite. So in this case, the u sub you likely do is with tangent, because that's the easiest, right? So easiest will be x over 1, not the square root of something over 1, right? That's pretty hard to do, to connect theta with x. So in this case, you have tangent theta equal to x, opposite over adjacent, and then in that case, to find the derivative would be secant squared x, secant squared theta, d theta equal to dx. All right. So here, let's relate the square root part back to theta too, because that's what we're trying to substitute. So in this case, it would be 1 over the square root part would be cosine x, right? Or you can just do secant theta, which is just the inverse of that. Either way is fine. Sometimes one might be more simpler than the other, but in this case, you can just plug the cosine theta in for this whole thing, and then you have secant squared theta, and then you can do math from there. I think you have secant theta, and then maybe you will be given what that integral is. But generally, you want to relate x to the theta as simply as possible. Right? You don't want to do like, you don't want to use this to relate x and theta. That's for the square root. That's to substitute the square root. But if you're using that to calculate dx, that's what we mean by relating x and theta, right? Calculating a derivative of this is really cumbersome, right? It's a 1 over like a square root, and that's not very nice to find. So find the simplest one. That's why we usually use like a number and just x to get that, right? With in the following examples, it might not be just 1, right? It might be 2, it might be like 8 if you have like 64, right? But that's still much simpler using that one singular number and just x or 2x than using the square root to relate x and theta.
For the next few cases, the square root part is going to be more complex, and sometimes you have more on top as well. Let's just look at case 3 with its so instead of like just x squared plus a perfect squared, like 16 or something, we have 4x plus 4. Right? In this case, we can look at this 4x squared as 2x parentheses squared. And in this case, right, instead of like our one side of a triangle here being just x, we have 2x and 2. So the hypotenuse in that way would just be square root of 4x squared plus 4. Right? You can choose this as theta. Ooh, that went a little too long. As theta, and relate x and theta sub theta for x in the original equation, and you should be able to solve from there. And then maybe you will encounter something on the bottom that's not just a square root. It might be some other power like 3 over 2. So in this case, right, you can separate that 2 out to be the square root. Right here, I have the x squared plus 1 uh, of square root, right? That just becomes a square root, and that overall to be um, the third power, right? So we still use the same equation to sub the square root part. As long as we separate that square root out, we can have like, because this part will be something like theta of something, and then you can, if it's like cosine theta, right, or it's sine theta, then it would be sine to the third power theta, and then in that way, right, you will be able to solve it later, right? Well, the trick of this is that if you have like 1 over sine theta to the third, and that's the denominator, so it's under like 1 over, then that just becomes sine to the third theta, right? And then that's just much easier. And then whatever you have for dx, like whatever d data is, and then that's just another trig integral that we talked about earlier. So and then the last case probably we'll encounter with trig sub is that you have something more complex um, in the numerator too, right? You might have like x squared x in numerator. The best tip I can give is that if you can simplify it anyway, right? If you're sharp eyes, this is a perfect square, right? It's x minus, or rather that should be 2, right? It's x minus 1 squared. Um, uh, both these should be. That's my bad. But it should be like minus 2x plus 10, right? You can separate 1 out here, and then you have x minus 1 squared, and then you have 9, which is 3 squared. And in this case, right, it's still the same, where if we separate like x minus 1 for u, right, it would be like a two-step u sub, right? You use u sub for a trig sub, right? Still have a theta, and then relay theta to u, and then solve it for theta, and then plug u back in, and then plug x back in. So that would be a little more. That would be a lot of steps, but with more practice, that can be actually not that bad. Right? And then the general idea of trig sub is that we have like sum or differences of squares. That's what you're looking for if you are trying to use trig sub, under a square root, that is. And usually it's in a denominator of sort, because if it's like in a numerator, maybe you're able to use u sub or some other way that's not as complicated to solve that integral. Thank you for watching this video. The past exam archive and all the videos I did related to this exam will be linked in the description below. Please check them out if you're interested. Thank you.